this page basically is a summary of the whole sections. Okay, all the math, all the key information, key formulas are summarized in this page, and I'm going to explain a little bit more with some writings. Okay, so this is our general schematic description of the systems. In general, we have K, we have a damping, we have mass. But here in this section in particular, we consider undamped systems, so we put C equal to 0. So this is a typical equation of motion. Okay, when we have the C equal to 0, then equation of motion is like this. The F of t can be any type of the force. And for harmonic excitation, that means the contents of the force basically is in pure sine, cosine or sine. Okay, the trigonometric functions. And that is a function of omega t. Omega is a working frequency. Again, we defined this term last time. Omega called the working frequencies. And working frequency is the design parameters. And that can be changed, depends on your design criteria. So omega usually can be given, say, by the designers, can be selected by designers, or omega can be changed such a way to minimize or to maximize some kind of things. Okay, so basically I want to emphasize is here omega is certain parameters, and most of the time that is a degree of freedom, not degree of freedom. Yes, I think that is a degree of freedom in design, and you can select. Okay. So here is a certain definitions, and here I put this one together. It's simply I want to build up good communications. Okay, so once we communicate with something, we better use these kind of standard terms. Okay, and so the first one, the FT, is called the external excitations, external force or loading. Okay, the omega called the working frequencies, and here the static diffraction. This is a very special term. That is simply is this. We look at this force. Right now, this is in harmonic excitation with a magnitude which is equal to F now. Okay, so we divide the magnitude of the loading with the spring constant. This is defined as a static. Why we call it static? Assuming if we don't have any harmonic excitation, that is a static loading. Okay, so that is the way we define this as a static diffraction. Okay, basically this term is the very special definition and only appeared in vibrations. But that term going to will be seen a lot later on. Okay, so static diffraction simply meaning is this term. Okay. We also will consider the frequency ratio. The frequency ratio, again, that is a ratio between the working frequency and the undamped natural frequencies. And again, this is a parameters. Depends on the magnitude omega we choose, then the ratio will be changed. Okay, so that is the parameters. And total response. And total response basically here is this one we call the total response, and that is combining, consists of the homogeneous solution and particular solutions. Okay, so that we explained last time. Homogeneous solution or particular solution, that is in terms of our DPEQ terminologies. On the other side, in terms of our vibration concepts, this is called a transient solution. This is called the steady state solutions. Okay, so basically there's a multiple names, but they indicating the same terms. Okay, and steady state solution or steady state response, basically that means this term. Okay, that is this term. And in these chapters, we're going to have a lot of the exercise, in particular dedicated to finding this term only. But in certain exercise, in particular in homework, I want to have everyone to expose to the full exercise. So sometimes I also ask you to calculate to determine the total response. That means the two terms. Okay. So from here we can go over with the certain writings and to reinforce our concepts in learning those things. So right now, I want to have a little bit a quick review saying how the two things been formulated. Basically, to this moment, everything has been reviewed already, has been done already, but we can do one more time and to reinforce our concept. Okay. So here we consider our equations, our systems. Mx double dot plus kx and equal to f0 cosine and omega t. Okay, so that is the system we're going to deal with. And this one, again, this is due to the externally applied force. The solutions basically were composed of the particular solutions and the homogeneous solutions. So they will say this is H and plus xpt. Okay. So for this one, this one is the transient solutions, and which obtained by solving mx double dot plus kx equal to 0. Okay. So that is the homogeneous solutions, and this one basically is our contents we've been exercised a lot in chapter 2. Okay, so for this case, we can right away to write up the form. Basically here, to get this one, you need to say, for example, to find the characteristic root, and then from the formation of the characteristic root, you need to write it up the solution patterns. So in general, that can be done by this. This is the natural frequencies, and say omega n equal to k over n, with determination of this one without damping, so that is a cosine, and omega nt plus c2 sine omega nt. Okay. And for xpt, this one's called the steady state solutions, or if you like, you can replace the solution, say the response. Okay. Sometimes the steady state solution, steady state response can be exchangeable in the description here. So this one really have to solve for is the particular solution that plugging into this, the left-hand side, and that will be equal to the right-hand side. Okay. The way to do this one is we have to assume. Again, back to the DFEQ, we assumed the appropriate type and then solve for that one. So that means the assumption of the form for this is important. And how do we assume the form correctly? That is based upon our knowledge or our learning from DFEQ. So here, from this moment onward, I would say when we say we take an assumed solution, I can tell you that assumed solution is correct one. Okay, and so here we take the xpt. Okay, and for this case, because this is a harmonic excitation, and for something to produce a harmonic function, that must at least have the same form. Okay, so we must have the same form, say cosine omega t. And that form must have the certain magnitude, and my magnitude will be determined by the operation of the system dynamics. Okay, at least we learned. And from earlier, chapter 2, we also, from DFEQ, we also learned that for any the harmonic excitation, that can be appeared in cosine or sine. So to make the things complete, usually we want to have the beta assumption, say this is the, say, let me say x, another, let me make it, okay, so another magnitude, unknown magnitude, multiply with, say, sine omega t. Only with cosine, in the combination of cosine and sine, that will make our assumed form complete, and that will satisfy this one. So that is the most general assumptions, okay? But I can tell you if you plug in the whole terms, and right now we're going to calculate is we're going to plug in. So that means then introduce xpt into our equations, the equation of motions. Okay, so we simply introduce the whole things into here, we see what happens. Here I can tell you this term x bar will be 0. Okay, I can tell you, but we can exercise at the first step. So xp double dot will be equal to, from here is minus omega squared capital X cosine omega t minus omega squared x bar sine omega t. Okay, so we have the double derivative, we have this one, we simply plug into there. So we introduce to there, so basically the two terms will become is this. That will be m. So from here, okay, so that means, let me do with something. So here we basically is m multiplied with this term and k multiplied with this term, then we take the summations, right? Right, because here we introduce this one and then that's the coefficients here. And the whole things must be equal to f now times cosine omega t. So that is our scratch. Then we can do the things with the term by term. So from here you can see when we take the summations together, we're expecting the left-hand side. So the right-hand side is f now cosine omega t. The left-hand side will have two groups of the terms. One group is about association of the cosine. The other group is associated with sine, right? Okay, so right now I know that one, so let me say that is the cosine omega t and with certain coefficients and plus sine omega t. Okay, now I'm going to work on the coefficient here. So that means for the cosine, that is the first one is k multiplied with all the terms, so that is a k times x, that is the cosine here. And k times x bar is a sine. Okay? And then plus the m multiplied with the cosine term is minus m omega squared capital X. Okay? And then sine m multiplied with this one will be good? Okay. So in this way, right now we have the equation equal sign, and left hand side is a combination of cosine and sine. Right hand side we only have cosine. So we compare those things term by term and with the coefficients. So that means here we have is this. For the cosine omega t terms and the coefficients equal to each other, so that means k capital X minus n omega square and capital X equal to f0, right? So right now we compare the coefficients. Of cosine and sine omega t. Okay, so right now for sine omega t, the coefficients basically is k minus n omega squared times capital X bar. And right hand side, there's a no sign, so that's equal to 0. So basically here I can tell you, once we assume this one, this is our assumed solutions. And for undamped vibrations, basically I can tell you this term will be equal to 0. I told you in advance, and that is our calculations, right? So for undamped solutions, for undamped systems, if the force excitation is in cosine, and here listen carefully, then you simply assume cosine form only. On the other side, if for undamped vibrations, if that force is sine, then you simply assume sine will be good. But generally, if you do this such a combination sine cosine get together, it won't hurt. but simply give you a little bit more rigorous, kind of a little bit more timing, the time in solution process, but eventually you will get it. Okay. Good.
Question?
Yes.
So that won't be true necessarily when we introduce damping?
Yeah.
Okay.
For damp system, the damp simply associated with the dot, the ddt. So this one, that means sine, for any sine function after derivative will become cosine. For any cosine function after this will become sine. So that means due to the damp term associated with the first derivative, we have to consider both. So therefore, from here, we have, let me rewrite here. So therefore, from here, we can know the capital X equal to F naught 0. So therefore, xpt will be equal to capital X, and X is F0, divided by K minus M omega square and cosine omega t. Okay, so that is the solved, the steady state response. Okay. And so right now we have individually come up with the form, and so let me erase these portions for. Okay, so that is a form. So basically, we take the both together, then that will come up with the total solutions. So therefore, the total solutions equal the total response. Xt equal to xh plus xpt. Okay, so basically that's a combination of the two terms, and yeah, let me write it up. Okay, one more time. C1 cosine omega nt plus C2 sine omega nt plus F0 K minus N omega square and cosine omega t. Okay, so if we have a problem, so let me erase the unnecessary informations. So that one we solve is this. Okay, so that is the key information. So let me I just erase unnecessary information. So that is the whole summaries. On the other side, I want to give a note is this. So say if we have the excitation, so say if we have excitation, say that is F0 times sine omega t. Then here, if that is a sine, then here that means xpt will be equal to the same magnitude, but in terms of sine, that will be multiplied with sine omega t. You know what I'm saying? Okay, so basically that is the two forms. I kind of put two forms together. Okay. And so so that is a note. But for our illustrations later on, I just stick with the cosine. Okay. So that is a total response. And right now we can look at the response, the written here, see the informations, because quite a bit parameters, the variables here. And one is we know that in cosine and sine, that is about the oscillation, it's about transient. And omega n, that is all natural frequencies. So that means we always can first calculate, get that number ready. C1 and C2 here are unknowns. So that is the two unknowns. Right now, we keep in mind we need to solve. Okay. And here in this way, the third term here, F naught, that is the magnitude of the given load. So usually F naught can be obtained from the given information. Usually we will assign it. So F naught should be a constant. And K minus M, K and M are constant at the given boundary problem. And how about the omega? Omega, that's a work frequencies, right? So again, I told everyone in the beginning, omega is a certain value and parameter we can choose. So that is the one you have the degree of freedom. You have a degree of freedom. You can monitor. You can govern the solution. Simply, if you change the omega, then at least this term, the value of this term will be changed, right? Okay. And again, this is omega t. And so the whole overall, in the total response, we still have two unknowns, and C1 and C2. And C1 and C2, two unknowns, how can we solve for it from the initial conditions, right? So here we with the initial conditions, say x0, let me put the generic, and that is certain numbers, and then the initial velocity, let me define as a v0, okay? So once we are given the initial conditions, the C1 and C2 can be solved by there. And how to do it, and again, this is the symbols. We simply do the symbolic calculations. So that means, let me skip out the detail, but because from grading the test, I think the majority of the people can do it very good, okay? So here we take the derivative. So if you take a derivative, then from here you can take the derivative of the whole terms, right? And then you simply plug in here. So just like our exercise. So for example here, that is omega n C1 and minus sine omega nt plus omega n C2 cosine omega nt. And for this term, that would be minus omega times f k minus n omega squared sine omega t. Okay, so with the omega, with the x and x dot available, you simply plug in the two numbers and solve for it symbolically. And that one is showing here. And plug in, summarize, and reorganize, then that will be the form. And this form appeared in our textbook. I simply type in and showing here. So that means if you wish to have the cheat sheet available to you, then you have to write down this one. Okay. On the other side, I don't recommend using this equation. At least for me, I never want to memorize this equation. Any good equation shouldn't longer than 1 or 2 inches. Okay. If that equation is longer than 1 or 2 inches, that shouldn't be treated as an equation. That should be treated as a symbolic calculation. Okay. Good equations and something like this one. That's a good one. Okay. So again, that is the result. And the result, basically, you can see here from your exercise, that is the result of symbolic calculations. If we are dealing with the numbers, and that won't take you too much time to just running through the numbers, and you will get something, right? Okay, so just exercise and take a little bit 1 or 2 more minutes, then just do the number crunching, solving the different equals, you'll get it. So as far as the availability of this equation, I think this one is really not necessary. Okay, but since textbook listed, I just listed here. Okay. So that's the whole thing, and so that is the whole scenarios of the fundamentals of the undamped systems. And again, here I want to emphasize one more time. For undamped system of the under harmonic excitation, they would have 2 possible forms, either in cosine or in sine. Okay, then simply follow up, then that is the particular or steady state solution that will be in the same pattern, cosine or sine. Okay, and that's the first note. The second note I want to make is about this form, about the magnitude of this. Okay, so for these terms, and these terms, we can sometimes you can directly work on this one, and sometimes we like to do certain dimensionless expressions. So this term have other possible equivalent expression, and we can do like this. And let me use green as this scratch calculation, or different color as a scratch calculations, and then I will write up the final form. Okay, so from here, this one, to get another format is this. We simply scale the numerator and denominator by k. So that means I divide f now by k, and the same thing, the denominator by k. Okay, so I simply divide the numerator and the denominator by k, and then let me rearrange the result. And so from here is f0 divided by k, okay, and then here is 1. I want to work on this one. So basically this one is equal to, here I put the inverse, so k over n. Be okay? So this one will become, by plugging into our definitions, so looking at, compared to our definitions of the term there, in this way, in our numerator, f now divided by k, that is our, we call the static diffraction. Okay? And 1 minus, so here basically these terms simply equal to omega squared divided by omega n squared. Right? This is our k over n is our the square of our natural frequencies. So basically, this is r. This is r squared. Okay. So sometimes people like to use this form because this form is, I would say, have a cleaner contents there. Okay. So that is the notes. So either format you will see from the textbook and even from the other book.